Hi, my name is Nick Reinhardt, and in this video, I'll talk to you about our research on learning a contingency planner from behavioral observations. What is contingency planning? Contingency planning allows for a robot to consider its ability to react in the future when deciding what to do now. This decision tree represents an autonomous driving scenario of possible sequences of robot and human decisions when a robot is trying to make an unprotected left, in which it does not have the right of way in the intersection and must wait for the oncoming car to either pass or yield before turning. If the robot were to decide ahead of time a deterministic series of actions, that is, a non-contingent plan, it would prefer to wait outside the intersection and never arrive early because of the unresolved human stochasticity. If the robot was overly confident in its ability to make the human yield, it could produce a plan that always turns before the human, but may lead to collisions in reality when the human does not do what the robot planned for it to do. However, with a contingent plan, the robot can potentially arrive earlier by planning to enter the intersection first with a contingency plan for different behaviors it may observe the human to do. If the human chooses to yield, the robot would proceed to make the turn. Otherwise, the robot waits for the human to pass. Why is contingency planning difficult? It requires a few key ingredients to work well. It requires a model of interaction between the agents. It requires the ability to use this model to produce contingent plans. And it requires the model to be seen conditioned, because the behaviors of the other agent, as well as the goal of the robot, both generally depend on the context of the environment. Our goal is to make contingency planning tractable by learning a latent planning space where open loop latent plans translate to contingent plans when combined with the uncertainty of the other agents. This will enable end-to-end contingency planning from high-dimensional observations of the environment and should minimize the engineering burden of planning in arbitrary scenarios. We have as input to our model a single latent robot plan, as well as some scene conditioning. The model incorporates as input uncertainty about what the other agents may do. For one realization of what they may do, the single robot plan results in a specific joint trajectory. For a different realization of what the other agents may do, the single robot plan results in a different joint trajectory. If we can design a model in this way, the challenge of contingent planning is reduced to the challenge of identifying a single robot plan in the planning space that results in high-quality trajectory space plans and expectation. This planning space corresponds to a small set of free parameters of a robot policy. Once these free parameters are specified, the robot's policy is fully specified and corresponds to a contingent plan. We implemented various scenarios that require contingent planning in the Carla simulator. On this slide, I'll present videos of each of the possible outcomes in the left turn scenario. The first video shows the outcome in which an aggressive robot turns unsafely in front of another car that the robot does not control, which I'll refer to as the human, and the human is unable to yield at time. The second video shows the same aggressive robot coupled with a human that is able to yield in time. The third video shows a passive robot that always waits outside the intersection for the human to pass. The fourth and fifth videos demonstrate a contingent robot that nudges into the intersection in order to observe whether the human will yield to it, and the robot reacts differently based on the human's behavior. The contingent robot safely and quickly arrives at the goal more frequently than the non-contingent robots. Here are the results of applying our method to contingently plan with the robot. Because it contingently planned, the robot enters the intersection in both cases and waits to observe the human's response. Here are examples of various non-contingent planners on the same task. An overconfident planner assumes the human driver will always cooperate and can result in overly aggressive robot behavior in which it always attempts to turn early. A planner that plans purely in the state space of the robot's future trajectory results in an underconfident planner. This planner causes the robot to wait outside the intersection until it is guaranteed that the human is no longer in it, since it cannot deal with the stochasticity of the human with a single state space plan. Here's another scenario, which features a right turn. The scenario is similar to the left turn scenario. An aggressive robot always turns before the human, which may or may not yield to it. The passive robot plans a single action sequence, which forces it to prefer waiting until the human passes through the intersection. The contingently planning robot enters the intersection with a plan for different courses of action depending on whether the human yields. These videos showcase the overtaking scenario, the final scenario. Here, the robot is trying to overtake the human by switching into the left lane and then passing it. While the human may slow down to facilitate the overtake, it could also choose to speed up to prevent the overtake. The aggressive robot always overtakes the human, which sometimes results in a near collision. The passive robot never overtakes the human because its single action sequence plan is deterred by the stochasticity of the human. The contingently planning robot enters the left lane with a plan for different courses of action depending on whether the human yields. If the human yields to it, it overtakes the human. Otherwise, it waits for the human to pass and re-enters the right lane. Here's an overview of our method from model training to deployment. The model is learned from two inputs: multi-agent demonstrations of behavior, essentially state space agent trajectories, and observations of the environment. In our application, we use LiDAR range maps. At the deployment phase, the robot repeatedly plans using the contingency planner. The contingency planner itself has a function that scores joint trajectories, and I'll discuss this later. The planner also receives observations as input, as well as past trajectories from the environment, as well as a goal for where the agent should go. The output of the contingency planner is a policy. The policy is used to produce the next target position of the robot, which is then fed to the simple positional controller on vehicle throttle, brake, and steering. The controller executes for one or several steps before repeating the above planning procedure. At the training phase, a deep likelihood-based model of multi-agent behavior is trained to forecast trajectories via a maximum likelihood objective. This model will form part of the contingency planning criterion, as well as represent some of the parameters of the policy that's planned at test time. Here's a diagram capturing the high-level architecture of our model, which is a flow-based model that transforms samples from an isotropic Gaussian distribution over the latent space into state space trajectories. It takes as input a high-dimensional observation from the environment, which in our case is a 2D representation of LiDAR. It then performs autoregressive one-step predictions for all agents. The output at each step is parameterized by a Gaussian distribution with mean and variance, output by recurrent neural network. And this model represents the robot's base space, the Z's of the robot. And these Z's constitute the contingency planning space at test time. A closed loop policy represents a contingent plan. We represent our policies with two sets of parameters: a small set that's planned at test time, the robot Z's, and a large set that's learned as part of the behavioral model. The stochastic policies in the model become deterministic when their uncertainties are specified. Thus, we can treat the robot's uncertainties as the latent planning space. Specifying them identifies a particular deterministic closed-loop robot policy. This policy is a plan to react to future behaviors of the other agents. The plan parameters are optimized via a gradient ascent objective, on our planning objective. This objective rewards plans that have high likelihood under a prior, which is essentially the model's likelihood function. And this planning criterion also incorporates the destination by awarding plans that result in trajectories that come close to the goal. Lastly, the planning criterion penalizes for any constraint violations like near collisions. The objective is to plan high quality plans under the expectation of the uncertainty of the other agents. In our experiments, we find that randomly sampling a large number of latent robot plans suffices as an approximate maximization method instead of gradient ascent. So if we return back to the diagram that describes the goal of our system, we see that the uncertainty of the world is a distribution over the free parameters of the other agents, and the latent plan for the robot is the specification of its free parameters. Together, these are transformed by the model to produce a joint trajectory. Here are visualized examples of contingent plans on the left turn task. The robot decided to nudge forward and act according to the human's reactions. Note that a contingent robot plan can only be visualized by combining it with the set of human responses, the specified human uncertainty. As we can see here, the contingent robot plan, which is an open loop plan, leads to closed loop control as it results in different state space trajectories based on the human's actions. Whereas planning a fixed state space trajectory will fail here because no fixed trajectory can navigate through the intersection given that the human is stochastic. Here are additional examples of contingent plans. For this overtaking task, the contingent plan tries to overtake if the human yields, and abandons it if the human doesn't. Note that these two sets of state space trajectories originate from the same policy. Resampling the human latent variables causes the policy to act differently to different human responses. For our experiments, we evaluated our approach on each of the scenarios we set up in a variety of locations in the Carla simulator. We compared against other approaches, including a single agent planner that doesn't model the other agent, the underconfident and overconfident planners, as well as another non-contingent planner, MFP. We observe the expected failure modes of each of the non-contingent planners, and we find that our approach outperforms other deep planning approaches on all three tasks. Thanks for watching. For more details, check out our project page and our paper and our code at these links. Thanks.